All right, thank you all for coming. Today we're going to be talking about deep learning. So this is the last lecture of the regulatory genomics and networks module. On Tuesday, we're starting to talk about population, genetics, and disease, and then the last module will be on evolution and comparative genomics. So on Thursday last week, we talked about network algorithms, including how to infer biological networks and how to process biological networks and how to analyze biological networks using a lot of linear algebra like SPD and sparse PCA, regularization approaches, kernels, and so on and so forth. Today, we're going to be talking about a whole different class of networks, which are probabilistic networks, which are going to be telling us about how different variables relate to each other. And in particular, we're going to be learning about deep learning, a field that has gained a huge amount of traction in recent years. So first, I'm going to introduce supervised methods for deep learning, then unsupervised learning using deep belief networks. These are, the first part is going to be about using input-output relationship that we're trying to learn. And the second one is just using input, basically trying to learn a set of nodes that somehow capture dependencies between variables and the inherent structure of the data. Then we're going to talk about a lot of recent advances in modern deep learning architectures, and then how this applies to the field of genomics and specifically regulatory genomics. And lastly, deep learning infrastructures. So what is deep learning? Why do we call it deep learning? Deep comes from the concept of having many layers. And these layers can be thought of as layers of abstraction. In particular, if you're trying to sort of learn something about an image, you could basically think of this as looking at higher and higher levels of combination of the primary input. In the case of genomics, the low level can be just DNA letters. And then above this, you could have motifs, which are made out of combinations of letters. And above that, you could have grammars. And above that, you could have enhancer regions or cell type specific constructs of maybe, enhancer level or gene level or any kind of higher order structure. And then ultimately predicting the expression of a gene or predicting the function of a cell and so on and so forth. And as you go further up these different combinations of input features, you basically can think of this as learning more and more abstract objects. In the case of images, this could be individual pixel values or edges in those pixels or parts of objects and ultimately objects. Who's with me so far? Awesome. So again, the visible layer is separated by many, many different layers from the output layer, which is ultimately doing the classification. And then in your training, you might sort of have examples of images with a car, examples of images with a person, and then the system will be learning at each of those intermediate layers more and more complex combinations of those input features. Everybody with me? So that's where the deep comes in learning, but it's also important to recognize what are things that are not deep learning. Basically, you hear these terms thrown around a lot about sort of AI being equated with deep learning or things like that, and the terms are not interchangeable. So deep learning is an extremely specific class of representation learning with multiple layers of abstraction. Okay, there are other types of representation learning which are shallow. And we're going to look at autoencoders, for example, and other different types of shallow learning is possible with fewer intermediate layers. And then not all learning is representation learning. There's a lot of machine learning that doesn't try to learn an inherent representation for the data. For example, regression is one such thing where you're just trying to sort of learn the relationship between two variables without necessarily inferring something more abstract. And then there's a lot of traditional examples of classical AI where nothing's actually learned. Things are encoded by an expert, and then the system applies a set of rules based on what it sees in the environment, and therefore it reacts to the environment. And that can be thought of as artificial intelligence, and that's classically being part of artificial intelligence, but not necessarily machine learning. You're not inferring these parameters from the data. Is this distinction clear? And you can think of the different boxes of learning, if you wish, as these gray boxes, where in traditional rule-based systems, you don't need to do any learning. You basically just have, some input, some hand-designed program that responds to this input, and some output. With classical machine learning, you basically have a set of hand-designed features, so you don't have to learn these layers of abstraction. The features could be hand-coded about, oh, I'm going to learn how to recognize edges by hand coding them. And then you can learn from these features, and that's sort of where the parameters that the system learns are in that gray box. But with representation learning, you learn both the features and how this mapping across features works. And with deep learning, you basically have not only the learning of the features, but the learning of many intermediate layers altogether. Everybody with me so far? Sounds great. So the question is, of course, how do we as humans recognize patterns? And that's a big challenge. If you look at, these data set of handwritten characters, you will basically see that, yeah, of course, this is a 0, this is a 1, maybe that's still a 1, and that's a 2. But, is this really a 2? And, is that really a 2? And so on and so forth. So if you see it out of context, it's very hard to recognize these characters. But we as humans have a way of recognizing these features systematically that comes from a lot of experience. I mean, for example, my kids, I don't know if they'll be able to sort of recognize some of these weirdly shaped numbers. My son is learning cursive right now, and to him it's a whole weird thing. And yet, adults are able to do this systematically because we've seen thousands of these variations, and we've come somehow learn features that are representative of different types of letters. So the initial motivation for the neural network field, which is the precursor of the deep learning field, came from studying the human brain and basically looking at what are the basic operations that the units of the brain carry out. And these operations are operations of addition, of threshold-based activation, of taking the maximum or taking the sum, and then propagating these from very small units arranged in the millions into other units, and so on and so forth. Okay, so this basic structure of a set of dendrites receiving information and then summing up this information over some kind of threshold function and then spreading that information through the axons of a neuron is effectively what formed the basis of this artificial perceptron, which was the very first unit that eventually became the whole field of neural networks and deep learning. And the basic idea there is very simple. You basically have some kind of output function z that you're trying to approximate based on a set of inputs x. And all of these inputs are basically weighed according to a set of weights, one weight for each input. And then you're summing these up, and then you're taking some kind of threshold above which you then fire. Okay? So that's sort of the basic artificial perceptron. And then what neural networks do and what deep learning does is arrange these individual units into fully connected stacks across many different layers in the same way inspired by the human cortex. So here's a 4 layers deep network where you basically have your input units fully connected to an first layer, fully connected to a second layer, fully connected to an output layer. So then what are you able to tune? You're able to tune these weights here, and given the right set of nonlinear functions, which are effectively the threshold of activation that you put that corresponds to these thresholds of activation of actual neurons in the brain, by adding not just a set of linear combinations, but also an activation threshold, you can actually approximate any ridiculously complex function. And that's the power and the beauty of deep learning. The fact that these models are extremely powerful. They can truly model almost any type of function. This function can be extremely complex, and yet the system has enough representation power, enough versatility, enough parameters that it can truly learn that. Everybody with me? So let's talk about this nonlinearity for a second. So, and of course, because these systems are so powerful, we're going to have to figure out a way to cope with that power. In the case of, I don't know if you've seen Rain Man, he could memorize everything, but he had a lot of hard time abstracting and sort of, you know, deciding these very basic, simple threshold functions. So we don't want to overfit either. So basically being able to learn an extremely set of complex functions doesn't necessarily, you know, make the system generalizable. So, you know, if you see a new type of sidewalk sign that basically says cross, you know, overfitting would be to do what Rainman was doing, which was, you know, start, stop, 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 as the light was blinking, as opposed to sort of realizing that, no, there's some kind of window within which you're going to continue walking. And in the same way, when we talked about k-means, we said that if I said k to be n, to be the number of samples, then of course I can learn how to perfectly capture any set of endpoints by putting a centroid in every one of those points. But the generalization power of that is 0. You don't, you know, you're not able to sort of apply that to new examples. So because these systems are so amazingly powerful, we're going to have to find ways of avoiding overfitting. And we're going to talk a lot about that, about how to constrain how much power we have. And there's a lot of ways of doing that by limiting the scale of the weight, by limiting the number of units, and so on and so forth. Okay, and of course, by setting it up with a test set, a validation set, and so on and so forth. Okay, so anyway, these can learn almost any function thanks to these threshold functions. So what are these threshold functions? The traditional one back from the 60s was a sigmoid unit that basically has very, very, very little firing from that neuron for a big, big chunk of the input spectrum. And then after some kind of threshold is crossed, maximal firing. And then you're saturated and you don't go any further, okay? So this equation that describes the sigmoid is basically, you know, just that. And it maps to a 0-1 interval and then complete saturation. Everybody with me on this function? Great. So different version of that has the same property of no output for a while, and then a threshold that you're crossing, but then continues to grow with more input. And that's basically the softplus unit, which basically has 0 for a while. I mean, it's this green curve here, which basically asymptotes to x equals y equals x, and then has 0 for, you know, large negative numbers, and then this smooth transition in between. Everybody can see that from the green curve here. And then the last one, which is actually very widely used in a lot of modern systems, is this rectified linear unit. So this has the same property of 0 for, you know, big range below the activation threshold, of y equals x going further on the right, and then a sharp transition between them where you don't have this smooth transition anymore, but by simply choosing 0 if it's less than your threshold, or y equals x if it's above that, okay? And then you can tune these to become truly any function, because that adds the nonlinearity term that you need. And then, of course, with linear scaling with all your weights, you can sort of tune these functions to be almost anything. Who's with me so far? Awesome. So this is the basics. These are the building blocks of a perceptron, the many layers, these activation units, and these non-linearities. Okay, let's now look at how we can do the learning part. Okay, the learning part is based on, you know, learning gradients of how is my, you know, score function responding to different settings of my weights. Okay. At the core of it is the concept that we can update the weights at the next time point based on the weights of the current time point. Okay, it's this iterative optimization. And how do we update them? Using some kind of derivative that basically tells us if I take the derivative of my score by changing my input weight parameters a little bit, in which direction do I get the highest gain? Okay, so you can imagine a smooth, output function of what is my score compared to my weight, and then this is usually an error term that basically says how different is my y from the function that I compute from my x's. So that's the delta error. And I'm basically taking that derivative with respect to the weight w. And because this is a multi-dimensional vector, I basically have this gradient of the error relative to my inputs. Who's with me so far on this one? Great. So then there's complications that you can put on top of that. You can basically say, I can adjust my learning rate. Maybe at the beginning, I want to have a very fast learning rate to explore the space really fast. And at the end, I can slow down the learning rate. Some kind of form of simulated annealing where I can decrease the temperature of a physical system as it goes to sort of help it, converge into stable states. Okay, so this learning rate parameter can scale this gradient. Another thing you could add is some kind of weight decay that basically says that as I go through time, my activation, my sort of scaling of these input values is getting progressively smaller as a way to sort of, avoid overfitting, as a way to sort of allow the system to converge slowly towards some maximum. And I could also include a momentum that basically says, if I have been changing in a particular direction, I'm going to try to maintain that direction as much as possible with some momentum. Okay? Who's 100% with me on this equation? Perfect. Good. So basically, we have the gradient descent, where the partial derivative of the error with respect to my current weights, some learning rate, which is usually very small, sort of I don't overshoot the optimal solution, a weight decay that penalizes large weights to avoid overfitting, and then a momentum, which is based on both the magnitude and the sign of the previous update. Okay, when the direction of the update is consistent, then I will converge faster. When I'm sort of shifting very rapidly, I will continue going the same direction a little bit with some slowdown. So that's gradient descent. It's a deterministic algorithm that basically says I will always choose the direction of that gradient. A probabilistic version of that is stochastic gradient descent that basically can speed up the computation by randomly sampling a subset of your input samples and then updating the weights using only that subset. The advantage of that is that you avoid running into pitfalls when you're always using the same deterministic algorithm. You can somehow run the algorithm multiple times and catch different local minima or local maxima, depending on which direction you're looking at, and allow the algorithm to find a solution more often and to not get stuck in degenerate cases. Okay. And then another version of that is online learning, where you update the gradient using only one training data point each time. Everybody with me so far? Great. So that's the learning part. And that's the learning for one of these entries. For one of those, I basically have some kind of output, and I can sort of scale it according to the delta of the error according to my weights. And I can do that, of course, across every node in my network in the following fashion, by basically first doing a forward pass where I compute the output for each of those. And I sort of have computed the, both the gradient and the error for each of those intermediates. And then I walk backwards from the output layers to basically adjust my inputs at each point. Basically, in order to sort of better match the output, I want to adjust those this way, which basically gives me a new set of values here, which gives me a new set of weights there, and a new set of values here, a new set of weights there, and a new set of values here. Everybody with me? So basically, this is the basic foundational approach for how you train a set of weights across many layers of this network. Sounds good? So all of this is very sort of classical. All of this, was worked out already in the 60s. Okay, and then the whole idea is that we have a provably improved prediction accuracy at every iteration, because whatever the error surface might be, we're sort of walking along that gradient, we can continue improving the function at every set. Okay, so at every iteration, the error derivatives will decrease the distance between the current weight vector from every local optimal solution. And after a finite number of updates, the weight vector will reach one of those local optimums, okay, because I'm walking along that gradient. There's a lot of challenges, of course. Basically, you have to sort of think about what is the shape of that optimal function and how narrow are these canyons of steepness that I want to climb to find that optimal solution. And there's a lot of things that follow from this intuition. So basically, if the optimal solution space is very narrow, convergence can be very slow because I'll be jumping up and back and forth all the time. The learning rate must be small to not overshoot, but large to actually eventually get there. Various numerical approximations can actually point to a slightly incorrect direction and then lose the optimal completely by sort of going away from it and never actually able to make it. With too many parameters and too few training examples, I might overfit and sort of have a solution that is not very generalizable. And if I tuned the inputs a little bit, I might get a very different solution. Also, large networks take a lot of time to train. They need bigger steps, but they can also shoot in wrong directions. And then learning of parameters is only the bottom layer in some systems. And then learning architecture is an outer layer loop where you basically can choose the number of hidden layers, the number of units, the learning rate, the weight decay factor, etc., as part of an outer loop that sort of says, okay, given a set of parameters, here's my optimal solution, but now can I optimize on those parameters as well? Who's with me so far? Awesome. Okay, so that's sort of the basic foundations, if you wish. And now the question is, how do you avoid overfitting? Okay, let's talk about what is overfitting. Overfitting, as I mentioned earlier, is when you have a huge expressivity power and you tune it so far that anything outside your training examples is effectively misclassified because you tune your power so much to those examples. Here's a very powerful illustration of that. So as you train, you will basically see that if I have a training set on which I am sort of fitting these parameters, I can eventually push this error all the way to 0. I can basically, given the power of these numbers of parameters, I can approximate almost any function almost perfectly. So I can bring this blue error all the way to 0. But if you now hold out a validation set that you can then use to sort of test your example or a test set, you can basically say, what is the error in green that I get on a separate set of points? And what you will notice that, yes, as you're training on the blue examples, the green example performance is also getting better. The error is decreasing. But after a while, that error starts increasing again. And that's the part where you're overfitting. You're basically now, instead of sort of learning a smooth separation between your positive examples and your negative examples, you're now putting a tiny little circle around every positive example, okay? And therefore, with a new set of data points, you're gonna be performing worse. Is everybody with me? So one way to do this is to basically separate, say 90% of your data, use it in a training set, and 10% of your data, use it as a test set. And then you train using only the training set. You never use the test set to train. You only train using the training set. And then your parameters are improving. And then you stop sort of fine tuning those parameters to your training set when your performance of the test set gets worse. Okay, so that basically means that only the blue guys are driving the performance, but instead of sort of stopping when the blue curve keeps going smaller, I stop when the green curve stops getting smaller. Is everybody with me? The problem with that is that I might be still jiggling around and end up with, I don't know, 20% error here, 30% error here, 16% error here. And I'm like, okay, great, that's the smallest, let's stop at 16%. But all the subsequent ones and all the surrounding ones were actually higher. And that could just be that the particular set of parameters that I ended up with, yes, minimize the performance on the test set, but it did so artificially. And the way to really evaluate that is to have yet a third part of your data that you're sort of holding to the side as your ultimate validation set. That basically tells you, if I didn't know the performance on the test set, what would it actually be wherever I stopped? Does that make sense? So you can leave out a small validation set. It's not used to train the model, and it's used to evaluate the model at each iteration, and that's sort of sometimes known as validation cross entropy, and you stop when this validation cross entropy increases, preventing overfitting, and you can use your validation set as a way to know what would it perform like in a new set of examples where I don't get to choose the stopping point in order to minimize that error. Yes?
What's the difference between cross entropy and error?
Very, very little. So don't worry about it. All right, so we talked about regularization in the last lecture. We basically said how in any kind of learning model, you can have a very large number of parameters, and one way to increase generalization is to penalize by the number of parameters. And we saw how you can use a linear penalty or a lasso penalty for, which is effectively the norm of all of your weights, or a quadratic penalty, which is the sum of the squares of all your weights, or a combination, lambda 1, lambda 2, scaling, the lasso and the ridge regression penalties, regularization penalties, which are which is known as elastic net, and so on and so forth. Okay, you can use exactly the same approach in neural networks. You can basically set constraints on the total sum of weights or the total sum of the squares of the weights, and so on and so forth, or a combination thereof. Another way to do this is to basically use something known as dropout training. That basically says, instead of regularizing as a way to keep my weights overall small, I'm going to regularize by zeroing out many of the weights. And one way to do that is to basically take nodes that have relatively small weights and just say, I'm not going to consider them below a particular threshold. Another way to do that is to randomly choose which weights you're going to throw out for different training examples. Okay, so as I iterate through my different training examples, I could basically have some probability of keeping different subsets of these activation units. The advantage of that is that it avoids that all of these weights are tuning to that function exactly. And it allows, of course, better generalization. And the way to think about this is that this is equivalent to a bagging approach or a bootstrap aggregation approach that basically has an exponential number of models, each of which is missing some of the nodes, and effectively using some weighted voting of all of these subsets of models on your final model. Okay, so you're basically training the subnetwork by backpropagation as usual with each subset of nodes for each training example. And then that is mathematically equivalent to having a very, very large number of networks, each of which has a subset of the nodes, okay, by sort of choosing them randomly for each of the individual examples. So that's a very powerful regularization method, and it avoids overfitting in practice. Okay, who's with me on the regularization and who's with me on the dropout? Yep, awesome. So then the result is quite nice. Basically, without dropout, you end up getting stuck at some performance, but then with dropout, you can get to a much lower error. Okay, so then this is your testing error, and then the testing error continues to increase after the non-dropout training has reached the plateau. Okay. All right, so that's supervised learning. That's basically when you have labeled data and you know what the label that you're trying to predict is. Okay. But these kinds of architectures of deep learning can actually also be used for unsupervised learning. And I'm going to go grab a bottle of water. I'm sorry. Oh, hold on. I paused the wrong thing. Let's see. Pause return. Everybody with me so far? Great. So now unsupervised learning is much more difficult. Basically, what you're trying to do is learn inherent structures of your data. But the same type of approach can be used there. How? By effectively having your set of input functions, of input variables, and having your set of output variables, but no training. You don't have an error. All you have is a set of hidden units which are trying to capture relationships between your input units. Okay, does that make sense? So this is actually known as a generalized Boltzmann machine, and we're going to talk about restricted Boltzmann machines soon. But this is actually a symmetrically connected network. There is no output. There's just these hidden units, and you're not reading them. All you're doing is sort of learning functions on the weights that capture the relationships between your input variables. And every binary unit makes some stochastic on-off decision, and the network weights learn the relationships between these variables as they're turning on and off. And the overall configuration of the network dictates the overall energy of the network. And at equilibrium, this network actually follows a Boltzmann distribution, which is this exponential negative energy distribution, which is some kind of energy from all of your visible and all of your hidden nodes. Okay, so then that energy function is simply the sum of your binary vectors, each multiplied by some state that you're in, and then every one of those states, which is the 0, 1 decision, is multiplied by a bias of every unit. Okay, so you basically have a bias term for all of your units, and then you have a set of weights which are learning the relationships between these units. Okay, so then these relationships is what you're trying to sort of minimize the energy of. Okay, and then your overall energy of the system is basically this probability function that basically tells you what is the energy when I sum over all of the hidden units, and also when I divided by when I sum over the visible and the hidden units. So given your set of visible units, the goal is to learn a set of weights that maximize this total probability. And that's where this Boltzmann machine becomes this universal approximator of probability mass functions over discrete variables. So the advantage is that there's a lot of local learning rules. Every variable is inferred based on only its neighbors. There's no need for example annotations. There's no output function. But the challenge is that it's very difficult to train. And the reason for that is that these hidden units are connected to each other. So every time this hidden unit is moving in one direction, it's pulling the other hidden units, which are in turn pulling it back, and so on and so forth. So that makes it very hard to train. That's where the restricted Boltzmann machine comes in, because it allows you to now remove all of these intermediate hidden variables, all the connections between the intermediate hidden variables and the connections between the visible units. And it effectively results in this bipartite graph that only has this one layer of hidden units, one layer of visible units, and this very simple unsupervised learning module. And this is actually much easier to train than this general Boltzmann machine because there's no circularities. So again, your objective function is dependent on both your visible units and your hidden units using exactly the same sum. But now this can be separated into simply this bias times the hidden units, this bias times the visible units, and then all of these weights with all of their pairwise combinations. Okay. So the problem is that this is still very, very large to estimate directly. So the best way to do that is to apply some Markov chain Monte Carlo approach or sub-Gibbs sampling approach to train different parts of the system at a time. And then these generalized and restricted Boltzmann machines can be stacked on top of each other with multiple layers of hidden units, and also with the ability to connect output functions on top of these hidden units. So in the same way that, for example, this dimensionality reduction and this singular value decomposition allowed us to learn combinations, linear combinations of our input variables, we can now learn these linear combinations of our input variables and then train something on top of those combinations. So you can use these generalized or restricted Boltzmann machine to basically learn a set of hidden variables that capture the relationships between your input units, and then learn whatever you would like to learn on top of those. Who's with me so far? Awesome. So you could also peek into what's being learned by generating outputs from this. So you could basically sample, you could let this network loose on a bunch of digits, for example, handwritten digits, and then see what it learns, from those samples. And what you will see is that as the network number of iterations increases, you will see that different ones of these input units are in fact learning how to classify different types of characters. And you can sample from this by, clamping down your input or your output and then asking what is the end result on the other side. So for example, if I clamp down one unit and I ask what are the sets of inputs that would lead to it, it can basically tell me what are the pixels that are contributing to each of those classes. And then I as a human can recognize the corresponding shape saying, oh, I guess these hidden units are now learning the pixels that contribute to that cluster, which actually corresponds to the 4. Everybody with me so far? So in the same way that we could learn the supervised training using gradient ascent, we're now going to learn these unsupervised units using these energy minimization. Okay? So basically what you have is this thermodynamic state of the overall system that basically tells me how are these individual units connected to each other and how are they responding to each other and to small perturbation. And you're basically trying to learn a function that minimizes the overall thermodynamic energy of your system. And the system can then settle down in a set of parameters for those hidden weights, for those weights between your visible units and your hidden units, that basically approximate some kind of function of that. And then these could basically reaching some local minimum energy or some global minimum energy. Okay. And the problem, of course, is that you might get stuck in a local energy minimum if you settle down too fast. And you might also just never reach these global energy minima. So one way to overcome these local minima is to basically have bigger steps at the beginning and smaller steps as the training goes on. And one way to do that is to basically have this virtual temperature of the system that you're tuning. And at higher temperature, bigger jumps are taken, and at lower temperature, smaller jumps are taken. Okay? And that's what simulated annealing does. It basically scales this Boltzmann factor by some variable t, which can be thought of as the temperature. And then the higher this t, the bigger the jumps that you can make are. And then as the t gets smaller, this effectively becomes smaller. Everybody with me? So then you can train this by setting one variable at a time, by basically sort of clamping down each one of those variables, and then refining these intermediate weights according to a particular setup of the system. Okay, so you start with some training vector, you update all the hidden units in parallel, and then you update all the visible units in parallel, and then you update the units again. You had a question? You could. So basically in the same way that, Markov chain Monte Carlo can have multiple chains going on at the same time and then combining them and reusing them, the same type of training can be applied here. Yeah. All right, so you can basically use the same approach of taking a gradient in the direction of minimum energy, and that basically that moves towards the stability of the system. So, previously we were taking the gradient towards minimizing the error of an output function. Now we don't have an output function, but we have an overall energy level, and then we can tune the weights to go towards that level. So basically we can, take the derivative of this overall energy stability of the system relative to the weights, and then sort of move in the gradient direction that gives us the stability. And in the same way that you can basically learn a lot about the world and then applied to learn particular classes, you can go through phases of this learning. You can basically have a wake phase where you're clamping the visible units with data, and then you're letting the weights be approximated and move the hidden units. And then you go through a sleep phase where you release the values of your input units, and you just let the weights propagate from the hidden units. And that allows you to sort of adjust the state of the system to better approximate these functions. So rather than only moving from the visible units back, you can basically go through these cycles of learning from data, and then quote unquote imagining or dreaming data, and then sort of clamping down the visible units again to sort of retune these. And that allows you to sort of get out of these local minima and sort of have better relationships inferred from all of these variables. Everybody with me? So these are all very classical algorithms. We talked about supervised learning and the basics of the basic building blocks of perceptrons, these layers, these activation units, and then learning by gradient descent and by backpropagation, about learning rate and dropout, and avoiding overfitting. We learned about unsupervised learning with these deep belief networks and these Boltzmann machines, these restricted Boltzmann machines, sort of stacking them on top of each other. And then how this learning is still using a gradient, but in the error of minimum energy. You could use Gibbs sampling to train those, and you can lower the temperature as you go, and you can go through these wake sleep cycles, okay? So let's now talk about sort of much more recent developments in the field of deep learning. And specifically, we're going to talk about autoencoders, about convolutional neural networks, about recurrent neural networks, and about transfer learning and generative adversarial networks. So the first very, very cool recent innovation that is worth sort of wrapping your heads around is the concept of an autoencoder. What is an autoencoder trying to do? It's basically trying to learn a lower dimensional representation of your data. So if you have an image of a cat full of a ton of pixels, I'd like to learn something about the pointy ears, the tail, the whiskers, something that is a conceptual representation of a cat. How do you do that? You could basically do that by teaching the system what a cat is, labeling thousands of images of cats or millions of images of cats, and then training your system to recognize those images. Another way to do this is to basically train the system to output the input image. So you have this very, very powerful supervised approach for gradient descent and so on and so forth. So you're trying to sort of learn a set of weights that best capture your output function. But if your input function and your output function are the same, it sounds almost counterintuitive. What are you learning? You could just say, if I have 2 million pixels at the beginning and 2 million pixels at the end, I can just have 2 million hidden units that all output whatever its input is. Okay, great, I'm done. But the trick here is that I'm not going to have 2 million internal nodes. I'm going to have a very, very small number of internal nodes. So I'm effectively creating this bottleneck between the input and the output. And this bottleneck has to still generate an image of a cat, but it can only do so in a much lower dimensional representation. So what I'm effectively doing is tricking a supervised learning algorithm to work in an unsupervised fashion by sort of coupling the input to the output, but constraining the model complexity. So this is the same thing as this Boltzmann machine that was trying to learn a lower dimensional representation of your input. But now, instead of just having, my input here, I also have my input there. And that lower dimensional representation comes from this bottleneck in the number of states. Who's with me so far? So pre-training with some restricted Boltzmann machine could be used to learn representations for future learning tasks. And then you can use the output of these restricted Boltzmann machine as the data for the training in the next layer of your stack. And after pre-training, you can unroll your restricted Boltzmann machine to create some deep autoencoder. And you can also fine-tune these using back-propagation. So instead of just only using supervised learning here, you could actually use unsupervised learning at the beginning and then take those outputs of your hidden units and then finish the training in a supervised fashion. Who's with me so far? Awesome. All right, so that's one recent innovation. Another one is the concept of convolution. What is convolution? Convolution is the concept of using multiple pixels of the same image or multiple genomic locations to construct a single number from those locations. So you're effectively convolving, which basically means blending together, doing some kind of operation with multiple inputs. You're blending together multiple parts of your input, okay? Why is this useful? Because if you look at any kind of image, or if you look at any kind of genomic data, you basically have a lot of structure, a lot of local information being shared. And you could have a deep, fully connected neural network on your 2 million pixel image, but that's basically 2 million times 2 million connections and weights that you need to learn. So instead, you could basically realize that there's a lot of structure in those images and that I could somehow compute things from them locally. That basically near the sky, there's bound to be some other sky, and near this flower, there's bound to be some more flower, and so on and so forth, okay? So the way to do that is to basically compute these convolutions, which are effectively functions that compute based on multiple nearby input units. And the nearby is extremely important here. So in an image, convolution comes from neighboring pixels. In the genome, convolution comes from neighboring nucleotides. Raise your hands if you're with me. Awesome. So if these are your source pixels, you basically have 3, 0, 1, 2, 6, 2, etc. This is high intensity, low intensity. Your convolutional filter could be a function that I compute on these coordinates here given by the middle pixel, using the information from all of the surrounding pixels. So I'm basically going to take 0 here, and then positive numbers there, and negative numbers there. This convolutional filter will have its highest value when I have high values here and low values there. So that will effectively be detecting an edge in my image, because that's sort of where there's low values here and high values there. Raise your hands if you're with me. Awesome. So what this allows me to do is have computation come from those local parts of the image, end up with a possibly smaller image that has now extracted some additional information by convolving multiple pixels in my original image. And I can do that in many different ways. I can basically have, sparse convolutions where I'm basically, computing this across, different locations. I could have sliding filters. I could have many-to-one mapping. For example, I could use an RGB channel and output a single output from that. I could have DNA methylation and gene expression and evolutionary conservation all outputs into a single channel. So this is extremely powerful. It allows you to do a lot of things locally. And I have to make sure that this is computable on the entire image. Sometimes it will result in a smaller overall image. Sometimes the borders will not be fully covered because I have to have enough space out there to apply them. And then the last part of these convolutions is that instead of just having only linear functions, I can also have non-linear functions. For example, I could take the max in that entire part of the space. So in the genome, as I'm scanning the genome for a particular motif, for example, I might only care that there's some motif in the 200 base pairs nearby. So I just need the max. I don't need to sort of count the number of motifs. So I could take the mean, I could take the sum, or I could take some kind of nonlinearity like the max. Everybody with me? So these pooling operations basically combine local regions into a single output. And the benefits are that you can now learn hierarchical structures. You can basically have, for example, a translation invariance. Whether my motif is here, my motif is there, the output function is exactly the same. It's invariant sort of where things are placed. and it adds a nonlinearity, and it also reduces the overall dimension of your data. Everybody with me? So basically, convolutional neural networks have this local connectivity, parameter sharing, and that allows you to sort of have these translational invariants. They have low-level function features that are actually shared, and that's sort of the structure. The pooling allows you to do hierarchical representations, and then training these GANs is the same as the classical neural network using backpropagation. Okay, who feels that they're learning stuff? Yeah, awesome, good. So the next one is, oh yeah, please.
So the parameters that you're learning there are the convolution.
Yeah, you can learn both the convolution functions and how they blend together in the overall output of the image. So I don't know how many of you have seen that every time you type on your phone, it gives you suggestions for what the next word would be. So basically what the system is doing is the same thing that's sort of found in many sort of text processing and language understanding systems, which is that they're actually building a predictive function which is temporal. It basically uses previous examples and previous relationships to predict the next word each time, okay? And then you can scale those linearly, applying the same function over and over again as you scan through a temporal data set. So this could be time course gene expression data. This could be locations along the genome. This could be words in a document. Anything that has any kind of order in which the examples appear is amenable to this. And the concept here is, for example, that you can learn grammars. You can learn the ordering of different constructs and then predict the remaining sequence by training on your previous sequences. So each time you basically have the previous and the next data points, and at each time point you're sort of scanning across your sequence, and then you can predict sort of the subsequent words this way. So these recurrent neural networks have been very, very powerful both in text and in genomics. You can basically train this large recurrent neural network using long-range dependencies, and this is possible through new types of learning algorithms, because backpropagation is actually quite difficult when you have these long-range dependencies. So there are different types of optimizers, different types of connectivity functions, decomposition approaches that allow you to sort of make this much more efficient. So this allows for very efficient recurrent neural networks that can train on the entire corpus of Wikipedia, the New York Times, NIPS, etc. And then there's a lot of additional information you can use to learn about those. The last advance that I want to talk about is both transfer learning and generative adversarial networks. So the concept of transfer learning is that you don't always have the luxury of a lot of data. In some cases, you have very few patients, and you want to learn something about, I don't know, the electronic health records of patients with a rare form of cancer, okay? Well, you could apply your deep learning methodology only on the patients that have this rare form of cancer, but you would not have enough training examples. Instead, you could first apply your neural network on a much larger corpus of, say, all patients at the hospital. And then you can learn a set of features that are useful for some kind of task. For example, you'd like to predict who's going to be sicker at the next visit, or who will take a particular medication, and so on and so forth. So you're learning a set of features, you're learning a set of intermediate layers, if you wish, using a much larger corpus. And then when your new patients come in for that rare form of cancer, you can use a partially trained system and then apply it to your new patients, and then finish your training using that much smaller set of data, okay? So one way to think about this is that you're first doing feature learning in your big corpus, and then in a new corpus, you basically do an adaptation phase where you replace the top layers of your neural network only, and you maintain all the other ones. So if we go back to that very first example of all of the different layers, in an image recognition, in a radiology example, where you're trying to detect that rare form of cancer from radiology images, the whole bottom of the stack is identical. You're learning how to recognize edges and bones and, features and points and so on and so forth. And then only at the end, you realize, you sort of learn about the differences in this. In the same way, I mean, babies learn how to recognize the world through, a lot of unsupervised learning at first. And then we're all getting really good at various supervised learning tasks. And then when we go to a new task, we already have a set of internal representations, which we can then use to adapt to the new domain. Yeah.
Just to clarify, when you say bottom layers, that's the layers closer to the input. Yeah.
Correct. So basically the layers that have the lowest level of abstraction. Yeah. Everybody with me so far? So what that results in your new data set is that you're both starting with a big jump in performance before you even start training on your new data set. You have a higher slope where you're learning much faster, and then you also can reach a higher asymptote at the end. Okay? So again, a very simple example could be that you have a lot of healthy subjects, you learn something about your brain, their brain or their radiology images, you learn a lot of relationships offline, and then your new examples, which can be sparser, come in, but you have already done a lot of these pre-training, and then you can apply your classifier to the new examples and of course test them in a new set. Okay, so you learn these intermediate representations or these abstractions from one task, and then you apply them to another task, which requires then pure training examples, and you can reuse the features unchanged or do a small amount of adaptation. So I could basically say, I'm just going to use this network as is, or I'm going to use this network as the initial training set of weights, which I can then refine. And then you can this works across surprisingly seemingly different domains, because all radiology images have something in common, or all images have something in common, and so on and so forth. Yeah.
Like when your domains are different, and also that your feature spaces in the data could be consistent, right? So like in that case, would you that be like so falling into like feature implication space? Or?
That's interesting. So possibly. Basically, if your feature space is very, very different, there's not much you can do. Basically, it won't really help that much. But the set of features can be, reusable across very, very different types of tasks. So, and as for imputation, you could think of it as partially a form of imputation, because you're learning relationships between these variables. And there, if you have partial data, you've learned these relationships already. So knowing only part of your data could be still okay, because you now have the relationships that are still inferring the same types of higher level information, even though you didn't learn these functions directly on the data. Does that answer your question? Great. Any other questions? Awesome. So then the last thing I want to talk about is these generative adversarial networks. So the idea is the following. I don't know if you guys have seen all these images that basically tell you this is a person that has never existed, where basically the system is learning how to generate examples extremely close to the other sets, but yet sort of bring them out of thin air. So how is that possible? You could achieve that by basically having a human curate the output of all those images and basically say, yeah, this doesn't look like a person, or yes, this looks like a person, and give a score to this generative network. Okay, so you basically have a set of features, you have a generative network that uses these features to then generate examples of a particular class. And then you could basically, provide feedback to that class. An alternative way is to actually build a second network that will do the feedback for you. So instead of having a human train the network, you have another network train the network. And you train that network to recognize the differences between real images and fake images. So if the discriminator becomes really, really good, it will push the generator to become even better. And as the generator becomes even better, the discriminator becomes even better. Okay? So all you need is a set of real images and these, these input functions and this particular coupling of these generator and this discriminator networks. And if you couple them in this particular case, you can train them both to become much better at both discrimination and generation. And that's how these, sort of images come about. So then the idea is that supervised learning can be very powerful, but expensive and hard to train. Instead, you can generate a neural network that provides the feedback, and you couple the generator and the discriminator to improve them both. Initially, this was used for generative tasks. It was basically, great, can I produce, I don't know, random virtual worlds where I can drive my self-driving car and sort of get thousands of hours of driving without killing lots of people. But now this is very widely used also for semi-supervised learning tasks and for reinforcement learning with a large number of applications. So as you're building your final project, you should sort of think about these types of architectures as one very powerful way to get better performance out of the system, not just for generating more data, but also for, all kinds of other tasks. Okay. So for example, if you have very few data points to start with, you could sort of generate additional data points by using the properties of the existing data points and so on and so forth. So that can be a very powerful way to then enable your system to be, effectively learn functions of real data in better ways. Everybody with me so far? All right. So now specifically for the field of regulatory genomics, there's been a lot of progress in building these deep networks and using them for very specific tasks. So here's one example by Barash et al. In 2010, so that's almost 9 years ago, looking at this tissue-specific splicing code, okay? So what's the idea? What you're trying to do is predict whether this exon will be included or not in a particular tissue. Your features are intervals of sequence surrounding this exon, your flanking exons, and also the sequence within the exon itself. So you basically could, within each of those, give the system a set of features, such as all previously known motifs that are associated with post-transcriptional regulation, the structure of the transcript in the target exon, in the adjacent exons. And then the system can basically take all these previously computed features and then learn what are the best combinations of weights that allow me to predict exon inclusion or exclusion using those features for a particular tissue. Okay, so as training data, I have many exons from that tissue that are included or excluded. And what I'm trying to figure out is build a predictive function that tells me whether that exon will be included or excluded in that tissue. Who's with me so far? Great. So this initial splicing code network basically had 1,000 RNA features and nearly 4,000 exons, and it was feeding all that into a large set of hidden variables and eventually outputting whether a particular exon will be included or excluded in each of 4 different tissues. Sounds good? So the number of hidden units was following some kind of Poisson distribution. The network weights were following the spike and slab prior, and then the likelihood was computed using this cross entropy approach, and the network weights were sampled from that posterior probability. Okay. So this network could then be used to ask, if I have a mutation, will it increase or decrease my exon inclusion probability? So you could actually predict the effect of a disease-causing mutation directly from the splicing code. You could basically score the splicing changes that are due to each SNP. You could basically train it on 10,000 exons, predict the 3 splicing classes across 16 different human tissues, using these thousands of features, which include both motifs and RNA. and then score the reference sequence, and then score the alternate sequence for all 700,000 common variants. And then you can calculate the splicing inclusion probability for each of those, okay? And then what you can end up with is what is the largest absolute delta in splicing to score the effect of the SNP. And you could do that for each individual tissue, or you could do that in aggregate across all tissues, okay? So you have an input sequence, a variant sequence, your computational model, and you can predict what is the effect of splicing, take the difference, and that gives you the impact of the mutation on the regulation. Everybody with me? So when you do that, you can basically ask, well, where do I find the highest increased inclusion or increased exclusion for every exon? And if you plot that across many, many different exons, aggregating the data over the exon body and over the flanking introns, what you can basically see is where, at what locations relative to the exon boundary, exon intron boundary, did I find the strongest delta. And what that tells you is where are the features that are the most, where are the SNPs that are leading to the biggest change in inclusion or exclusion. And what you see is that as you get closer to that boundary, that magnitude increases dramatically. And as you would expect, because this is trained on existing exons, the drop in the score is much more likely. Basically, this is where exon inclusion will be less common, okay? Most often if you disrupt some of the signals associated with splicing. But also within the exon itself, there were a large number of SNPs that were affecting not just the protein coding sequence, not just the synonymous sequence, but also the splicing, okay? And that's, you know, very important to recognize. So that basically seems to work. It basically says that the features that are having the most impact are indeed where you would expect them to be. And if you now compare this to known genetic variants from genome-wide association studies, which we're going to talk about next week, you find that all of these genetic variants that were previously associated with disease had much bigger impact on the score. Okay, if something was disease annotated, you had much more, much stronger regulatory impacts. Sounds good? So if something was known to be causal, the regulatory score was much larger. If something had been validated in vitro or in vivo, or if it was associated, you basically had very significant increases in the probability that the system would predict it to be disease causing. So they also went in to validate by RT-PCR, reverse transcription polymerase chain reaction, you know, the impact of new mutations that were predicted to have a splicing effect, and they found that indeed they validated dramatically well. Okay. So this was a single hidden layer. The next generation, they went to a deeper network where they had additional hidden layers, enabling sort of higher order structures to be learned. But then this approach still had a lot of limitations. So you basically required to define discrete splicing events. It wasn't an inclusion, exclusion probability or a score. It was not taking into account the exon expression level. It was only saying yes or no. It was a fully connected network, which imposed a very, very large number of parameters, so 13,000 parameters. And then another big limitation is that the features were actually predefined. You could only use existing motifs. It wasn't learning those convolutional filters, if you wish. It was simply saying, well, here's a bunch of motifs that we know about already. Why don't you use those? And then, of course, the interpretation of the model was very difficult because you had thousands of predicting variables for any one exon. So it was very difficult to sort of, you know, understand what is actually going on biologically. So a lot of these issues were addressed in sort of subsequent regulatory genomics approaches for splicing and for regulatory motif utilization. And these were actually allowing to directly learn these internal motifs and representations, okay? So we're gonna basically talk about them in the context of these convolutional neural networks as these convolutional filters, okay? So in the same way that they're gonna have a 2D image and a filter applied to the pixels of that image to compute an edge, as we saw earlier, or a point or a shape or a corner and so on and so forth, I can use that to compute occurrences of a motif. How can I do that? The first one is this way of encoding DNA information as an image. Instead of having a one-dimensional vector, I'm going to have, one-dimensional input, I'm going to have a four-dimensional input, where every letter is encoded using this quote-unquote one-hot coding of the A or the T or the G or the C lighting up the corresponding pixel location. So if I want to encode a motif, which is ATG, CA, GCA, I basically can encode it in this particular fashion, okay? And if I want to encode my sequence, I can also encode it in exactly the same fashion. Everybody with me so far? So I can basically take my input sequence and I can represent it as a 2D matrix. And now I have my input sequence here, for example, and I want to score this convolutional filter in the same way that convolutional filters can recognize an edge. Now they're recognizing a motif occurrence. So the motif can be, for example, GC, A or G, G. Okay? And as I scan this particular convolutional filter on my sequence, for example, my sequence could be ATGCA, GCA, ATGCA, GCA. I'm scanning now this convolutional filter across the sequence. And in the first position, I have 0, 0 here, but the G lights up. And in that position here, I have GC, A, G all lighting up. And then I can have a score based on how well did my filter fire at each one of those locations. And then I can basically say that, well, the best motif match appears to be here. That's where my convolutional filter has the highest output value. Raise your hands if you're with me. Awesome. Okay, so now we can basically use that to build up our neural network. Any questions?
Isn't that kind of just like Gibbs template?
It's the same methodology, but now you can use all of the tricks of neural networks to basically fit a learning framework with gradient ascent, with learning these convolutional filters, etc., rather than, you know, just doing deep sampling. So basically, you could have higher level features learned from your lower levels, and that's the whole point of doing this. So if you only have the lowest level, yes, it's exactly Gibbs sampling. But the moment you have multiple hidden units or hidden layers, you can then learn grammars and combinations of motifs and so on and so forth. Does that answer your question? Great. So let's do that. Let's basically now build these sort of pooling operations, okay? So pooling operation could be a summary of each channel by either maximum or average. So you could basically run your convolutional filters, and then you could basically take the maximum over multiple motifs to basically say, did this motif occur in that whole sequence at all? Okay, so that's where things become really interesting, because you can sort of start asking about, you know, presence, absence, about combinations of motifs, about ordering, and so on and so forth. So you can basically train your convolutional filters, i.e. motifs, using ChIP-seq or protein binding microarrays or SELECT experiments, and then you can couple them together using these convolutional modules, these max operations. You can basically put multiple hidden layers in the middle, and then have your input sequence produce an output, which is effectively the affinity of a particular regulator to a particular DNA sequence. And that affinity could come from individual motifs or combinations of these motifs or higher order structures of the motifs. Sounds good? So basically putting it all together, this is what we have for deep bind, for example. You can basically have, you know, motifs that are trained from all of these sequences. You can then have, you know, your GPU compute convolutional filters from those, and then apply them to a bunch of different tasks. And then at the core of this machine, you basically have DNA input sequence, those motif detectors, which are your convolutional filters, that are scanning for motifs, your ReLU units, which are basically deciding whether a motif passes a threshold or not. So you can have 0 for a while, and then as it passes the threshold, become non-zero. And then you can pull them together by looking at the maximum of all your convolutional filters to basically see if any of the motifs that recognize that factor, that are recognized by that factor, are occurring in that sequence. And then you sort of learn your weights with which you're combining each of your motifs, and you have your output. And then, of course, you use back-propagation to then update all of the corresponding weights, update the motifs, update the combinations, and so on and so forth. Everybody with me? And then you basically can apply that to understand gene regulation, to understand the impact of individual nucleotide mutations, to recognize the binding sites of different proteins, and so on and so forth. Okay? Who feels that they're learning stuff? Awesome, great. All right, so using that, you can now construct a mutational map that basically tells you, if I have my reference sequence and my alternate sequence, what is the impact on my overall binding model of changing a single one of these nucleotides. And then I can infer what are the nucleotides that were the most important. I can recognize the motifs associated with the sequence. I can infer what are the individual mutations that will have the most impact on my overall regulatory score, and then apply that systematically, not just to existing mutations, but to all 3 billion times 4 possible, or times 3 possible mutations in the human genome sequence. Okay, so I can basically scan the entire genome and figure out what are the locations where mutations matter a lot. And that's important because in cancer, for example, I might have a mutation that I've never seen before. I can't simply test every mutation in the human genome experimentally. I could test every common variant potentially, and there's only 6 million of them or so. But I don't want to test all 3 billion times 4 times 3 mutations. Instead, what I can do is basically learn from the entire genome these predictive functions, and then computationally infer the score of every one of those mutations. Yes?
Yeah, I'm just thinking about how you can predict if a mutation occurs in a site that it will be pathogenic. Is there a way you can predict either the expressivity of such a mutation? Because, well, in addition, what do you do to control for potential sequence artifacts? I suppose this model doesn't have a problem because this model assumes whatever mutation it imputes is a real mutation. But what if, how does it then go? I guess maybe that's on the other side.
So if you think about it, sequencing artifacts are equally likely to occur anywhere in the genome.
Yeah.
So yes, you will be fooled by them, but only to a much, much lower degree compared to the actual mutations that are happening in places that really matter. So yes, just by chance, you might end up in one of the 100th of the spots where you basically have impactful mutations, but 99% of the cases will be falling in places that don't really matter. And in those cases, when you find a pathogenic mutation, you usually go back and resequence it. That's the first thing you do. You go and validate it. So you can basically predict which are the ones that will be the most impactful. And after you've done this prediction, say, wow, I think that there's something really going on in that patient here, you go and resequence it.
Mm-hmm. And how similar are some of these predicted pathogenicities to previously established pathogenicity scores?
They're actually much, much better. So, yeah, no, these systems have really made a big impact on accuracy of classification. All right, so basically the key deep learning techniques are these convolutional learning of basically combining multiple positions together to predict an output, and that's sort of the motifs. Representation learning, where you're learning in the first layer motifs, the second layer combinations of motifs. This back-propagation stochastic gradient ascent, that is basically optimizing the weights and the parameters and even the convolutional filters. Regularization and dropout, that allows you to sort of cut out outputs that are just too low based on your activation thresholds and these ReLU units. And this parallel GPU computation, which is especially useful for hyperparameter tuning of sort of the optimization of the model itself. There's of course limitations where you require some negative training examples. Basically, you're doing a classification between things that are truly bound and things that are not bound. And the things that are not bound can have a huge influence on the weights. Basically, you choose 300 locations that are bound and 300 randomly chosen locations that are not bound. to do your discriminative training, but those 300 can have a very big effect on what your learned parameters are. It's also using observed mutation data only after the fact to evaluate, rather than before, to basically make it part of the model. And then every regulatory data set was in fact modeled separately. There was no joint learning. So DeepC is another one of those models that is basically trying to go beyond that. It's very similar to DeepBind, but it's training using a separate convolutional neural network for each of the epigenomic chromatin profiles of ENCODE, so 125 DNase features, 690 transcription factor features, 104 histone features, and then it uses this delta of the score on each mutation as an input to then train a linear logistic regression to predict directly the impact of genome-wide association studies and EQTL studies from an existing database. So it's basically saying, well, I have databases where I know these SNPs have an effect. I'm going to train a model that optimizes these features to specifically capture known disease-causing mutations. So instead of just training now to predict binding, you're training to predict SNPs that matter. Everybody with me here? So you can basically learn these features on the reference allele and the alternate allele, look at the differences, and then sort of feed all of that into an overall score that then trains a classifier to predict disease mutations directly. Bassett is sort of a very elegant approach to do all this, where you truly have a deep neural network. You basically have multiple fully connected layers. You have convolutional filters that are learned completely de novo from the DNA sequence directly. You have this one-hot encoding, as we saw before. You have these rectified linear unit and these maximum pools to basically decide where motifs are occurring within sequences. And then this is actually using multitask prediction. The goal is to then learn a single regulatory alphabet for all of your experiments at once. And the advantage of that is that your set of motifs will be common among the different experiments. You're not going to learn different versions of the same motifs over and over again in each of the prediction tasks. Instead, you can learn a common motif alphabet in your convolutional filters, and then apply that to combinations of motifs for different factors at that layer down here. Everybody with me so far? So again, this is performing extremely well, and these convolutional filters, 300 convolutional filters were used, and the output of those convolutional filters, when represented as a motif, in fact matches many of the existing motifs in the regulatory grammar of human. Computer is trying to basically do this multitask learning as well, using these two layers, and then using a set of convolutional filters that learn directly a set of motifs, but then using a second set of convolutional maps that learn different shapes of chromatin. So basically now you not only have inputs that are sequence patterns, you also have inputs that are DNA accessibility patterns or histone modification patterns and so on and so forth. And that's very powerful because you're using the maximum amount of information from your underlying sequence. And some of these things might be not easily captured by the DNA sequence, so you can actually have an advantage of combining both. Does that make sense? Anshul's group also developed a way of visualizing these output functions. You can basically look at the back-propagation differences of your outputs using observed versus referenced inputs to obtain the gradient with respect to the input. And that basically tells you the importance of any input to any output weighed by the input itself. And that allows you to basically then visualize which nucleotides in your input sequence are in fact contributing to the binding prediction directly. So therefore your neural network is not a black box anymore. You can read the features that it is recognizing directly. And you can couple that together to learn complex grammars in the higher order layers of this network. Beyond DNA sequence, you can use deep learning in many, many different places in the field of computational biology. You can use that for protein DNA interactions. You can use that for protein folding predictions. You can use that for even designing molecules with particular three-dimensional conformations. So here are some examples from Thras-Karidis that's basically learning protein structures for families of proteins that have common functions, and using these, convolutional layers and these sparse codings across multiple intermediate layers to predict the the classes of proteins that are, for example, cutting DNA. And then what comes out of this system are lower level layers that are basically learning basic building blocks, and then convolutional layers that are combining these building blocks to ultimately learn structures of the protein that are recurrently performing the same function. So these latent representations of these structures can then perform a classification of the target DNA sequences of these proteins. You could basically say which proteins will recognize what features. So when we talk about zinc finger domains and talons and so on and so forth, you're going to see how difficult it can be to predict the binding sequence of a particular structure, but this kind of system allows you to sort of directly learn it from examples. So what we talked about was supervised learning, unsupervised learning, a lot of modern deep learning architectures, and specific examples in the field of genomics and computational biology more broadly, where these can be applied. I want to finish with some examples of how do you go about coding this, so that it's not just this vague concept anymore, but it is easily applicable to your projects and beyond. So the concept is that there are many different libraries that allow you to do automatic and symbolic differentiation on computational graphs for backpropagation. Many of them are compiled directly to graphical processing units, enabling speedups that are enormous compared to traditional machines, and that also allow parallel and highly optimized implementations. And you can have on top of that high-level libraries that wrap on top of these low-level systems like Piano and TensorFlow that greatly facilitate creation of these neural networks. And you also have very powerful GPUs. You can have GPU computing platforms as part of Amazon Cloud, and so on and so forth. So basically knowing this arsenal of tools can really help you make really great progress. So here's one example of how you would code a one-layer convolutional neural network with a binary output, okay? So basically you import Keras, which automatically imports the Piano and TensorFlow on the back end. You then import this 2D and convolution 2D pooling, max pooling. And then you import a sequential model, and then you import activation, dense, dropout, flatten, permute, reshape, and time distribute. And then you choose your input shape. For example, it could be 150 nucleotide segments with one hot encoding of DNA, so 4 variables, four vectors of dimension 4. And you can basically declare that you want 10 filters, and then convolutional height of 15, and convolutional width of 4. And so basically this is the size of your motifs. And then your batch size of 1,000, 20 epochs, and so on and so forth, okay? So you then initialize your model by calling the sequential function, and then you add this 2D convolutional filter using these parameters and your input shape. And you then add an activation unit, this ReLU activation unit, so this rectified linear unit that basically has 0 before and then y equals x after 0. And then your max pooling with whatever pool size you determine. Then you flatten the model, you basically have some output dimension, and you choose your activation function, which could be a sigmoid, for example. And then you can choose your optimizer and your loss, so you can basically compile the model according to that optimizer. And then you basically just fit the model. You say, here's my x, here's my y, here's my batch size, my number of epochs, and it just trains the model. You don't have to just go and sort of code every single weight optimization, gradient descent, or anything like that. And then your prediction is simply whatever the model predicts from your x according to your batch size. Who feels that they learn stuff? Yay. All right, so go out and do it. This is basically deep learning in a nutshell. So supervised learning models, the basic building blocks, the layers, the activation units, and then gradient ascent, propagation, dropout. All of these things are extremely important to learn, conceptualize, understand. This unsupervised learning version where you can train with energy minimization rather than an output function. These modern architectures of autoencoders, convolutional networks, recurrent networks, transfer learning, generative adversarial networks, and then different examples of deep learning in genomics. We looked at the splicing model, DeepBind, DeepSeq, Basset, and then lastly, how to apply this to both protein DNA and other structural applications. And then how do you actually implement it in practice? Who feels that they've learned stuff? Yay, awesome. Great, thank you all for coming. And then see you tomorrow.